We've gotten to the unit on momentum, and we've been talking about impulse as well. Well, now we need to talk about conservation of momentum and when things collide. Let's get to it. Conservation of momentum basically states that the total momentum before a collision between two objects is going to end up equaling the total momentum after the collision. That's it. But this can only be true if the only forces acting on the system are internal. So what does that mean? We know that when two objects collide that we have the action-reaction force pairs. That's Newton's third law. And we know that they're going to collide, and because of those forces acting on the objects, they can change their state of motion, meaning speeding up, slowing down, going from rest to movement. That has to do with, of course, Newton's first law, that objects resist that change in motion. So you need these internal forces to make it happen. So again, during this collision, those net forces act on both objects. That's important to remember. When we talk about conserving momentum, we have to define our system. And in this case, that's just the objects that are interacting with each other. So if you were to be at a bowling alley, we might say that our system is our bowling ball and our bowling pins. And the forces in between them, would be what we would be studying. Maybe it's the hockey puck and the hockey stick. Those two experience a force between them in an action-reaction pair kind of way. Only looking at those forces within that system would allow us to have conservation of momentum. Now, momentum's never truly conserved on planet Earth and the universe because there's usually external forces involved. And those things can be anything from like friction to air resistance, etc. But when we really just look at the total system, we can say if it's just internal forces acting on it, then momentum is conserved. Now you may say, well, how is it conserved? The two objects are running into each other. Maybe one object is not moving, the other one is. How do we really look at that? Well, we could say that the momentum lost by one of the objects would just be equal to the amount of momentum gained by the other object. So there's shifts in momentum. But needless to say, when momentum's conserved, the initial momentum is going to be equal to the final momentum. There's a quick question two people were asking about the fact that how is impulse really related to momentum? Well, if you look at their units, they actually end up being equal. Impulse has force times time, which ends up being Newton seconds. But when you break Newtons down into its kilogram meter per second squared and you multiply it by the seconds cancel out for the second squared and you're left with kilogram meters per second, which is exactly what you get when you multiply mass times velocity. You'd get kilograms meters per second. So they do end up equaling each other. So impulse definitely is the same as the change in momentum. And that'll be important because that can help us figure out things at times when we're looking for the change in momentum. Non-sticking collisions are something we should talk about. That's when a car runs up to the truck, bumps into it, the truck starts moving forward, and the car bumps away or bounces off, basically. When two objects collide and don't stick, we can look at that and say that the conservation of momentum holds true, but the loss in momentum from this car is gained by the larger truck. If we have two objects that hit and don't stick together, we can use the conservation of momentum to our advantage to use this formula. This is the momentum of the first object initially and the momentum of the second object initially. And when they bounce, since the velocity will change, its final velocity will be different for the object number one, and object number two's velocity will change, but they're set equal to each other because of the conservation of momentum. We can use that to calculate some things that might be missing from our information or our data table. Now, sticking collision difference are a little different. Perhaps this car runs into this truck, and the truck is in neutral, and then they start moving forward together and sticking together at the same time. If that's the case, we call that more of a sticking together collision, and we can think about that with the conservation of momentum. we would use one of these two equations. If you bump and stick together at the end, notice their final velocities will be the same at the end, so you just need to add up their total mass and multiply it by their velocity to get the final momentum. Obviously, their initial momentums would be separate and different, but since they stick together at the end, you can just find their momentum combined. Now that's a little different if the objects are stuck together in the beginning. Say you are on a surfboard, so you and the surfboard's mass combined with the velocity give it a certain initial momentum. But after you jump off the surfboard or you fall off, your momentum and the surfboard's momentum are slightly different. But added together, that gives you your total final momentum, which should be theoretically equal to your initial momentum, of course, if we're ignoring external forces. So, whether you stick together at the end or in the beginning, we can use these equations to help us solve for missing pieces of information. Either way, the equations look very similar throughout. We just have to know if the objects are bouncing. If they are bouncing off each other, that's more of an M1, V1. M2, V2 is equal to, again, M1, V1 plus M2, V2. And again, these initial velocities are in the beginning and final velocities at the end. And then don't forget these guys. If you stick together in the beginning or the end, you're going to use one of these. Either way, technically, if you used this very first equation we talked about, since the two objects sticking together would maybe have the same velocity, you could use this equation all the time and still get your answer. You just do a little extra work, but in the end, it gets you the answer. So today we talked about the conservation of momentum, and the idea here is that if you have all internal forces, the momentum of the system in the beginning should be equal to the total momentum of the system at the end. That just might mean that some objects lose momentum while the others gain. But in the end, it all works out. Thanks for listening. Best of luck.